Okay, example 6 is another symbolic problem. It says for rationals A and B, or for which rationals A and B does the following system have no solution, a unique solution, infinitely many solutions. Okay, so we have this A here, which is an unknown parameter, and that B there. And so again, we have to set this up symbolically, and we'll have to do our row reductions sort of by hand, but have the have Sage calculate that for us. And so we'll need to enter this augmented matrix, which I've already done just to save time. Now, so here are those swap commands so I can remember what those are. Here's the actual example then, and I set up my symbolic variables A and B. Now I have a space here because we're going to need to come back and set those equal to some constants to solve this problem. But here's our matrix, and you know I could make that look a little better by doing it this way and see everything match up nicely and check that against our work here. So 1, 2, 3, 4, but you know all negatives down here. That's 1, 2, 3, 4, and then 2, 3 sort of like 4, 5, and then 3, 4, 5 sort of like 6. So you know I can kind of check those, and yeah, those are all negatives. And it went 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, and sort of like 6. So yep, that looks good. And so I say show A and evaluate. And there's the A matrix, and I see what I need to do is get rid of that 2 and get rid of that 3, make those zeros. So one operation is going to be to take -2 times row 0 and add that to row 2, and another one's going to be to take -3 times row 0 and add that to row 3. So you can actually do both of those. So there is my row 0 times -2 added to row 1. Then I show the result. I don't necessarily have to show that result. I could keep that out of there so I don't have as much printed out down here. But you know, I'll do it just so we can see. And then here I have my last row, row 2. And I add to that -3 times row 0. So I evaluate and see that got the 1 0 and that got the other 0. So again, I didn't necessarily have to print this out since I did both of those at the same time, but it doesn't hurt. So now as I look at that, that's a 1 in there, which it's supposed to be, so that's great. And so the next thing I have to do is get rid of that -2 and get rid of that 2. So if I take 2 times this middle row and add it to this row 0, I'll get rid of that -2. And if I take -2 times the middle row and add it to row 2, I'll get rid of the +2 there. And so again, I can set up both of those at the same time. And when I did this, I did them one at a time, I think, and so I showed the result each time. But again, I don't have to. You know, I could come back here and get rid of that one, and come back here and comment that one out so I don't see it. So a comment is just this pound sign, or hashtag, as you might say. And so again, I evaluate. And so there's the 2 zeros there, so that column's done. Now this column is done, and I get to here. And now, though, I can begin to answer the question. So what would make this inconsistent? See, at this point I have these variables, and so what would make this inconsistent would be if this -2a plus 8 is 0, but b minus 6 is not. And so to be inconsistent, we would have a equal 4, because that would make this 0, and b not equal to 6. And if we go back here and try to find their solution, so here's a equal 4, and then they say if b is not equal to 6 for a equal 4 here, we get no solution. It's inconsistent. So that's the case back here where it says figure out where it's inconsistent. No solution. Okay, so that would be no solution. And then if a equals 4 and b does equal 6, then we get 0 equals 0 down here. Both of those will be 0 if we come back here and look. We get 0 here and 0 there. And so that's a consistent system if a equals 4 and b equals 6. And then if a is not 4, then we should be able to reduce here, and in that case we will get our unique solution. So let's we can do this a couple different ways. So we can go back here and say, okay, what if we let a equal 4 and we evaluate. Now we got an error last time, but notice, see, this time, this is why I was quite confused in the previous example. This worked just fine, setting a equal to 4, and notice that this looks like we would get something inconsistent. Let me let b equal 1 or something like that, anything but 6. If I say b equals 1, put a space in there, and evaluate, then you see we have an inconsistent system. So that would be a problem. But on the other hand, if I come up here and say let b equal 6 and evaluate, we get our 0 equals 0 and everything is fine. In this case we have an infinite number of solutions because z here is arbitrary, and we could write that down, right? We have x minus z equals -2 and y minus 2z equals -3. So z could be arbitrary, and we have an infinite number of solutions in that case. Now if we just get rid of these, okay, and we now we rescale. So here we are. Oops, I need to reevaluate so I can see what we had. Okay, here we are. I need to make that a 1, so what I need to do is multiply by the reciprocal of this thing, the -2a plus 8. And so that's the rescale part here. I just say rescale the last row, row 2, by the reciprocal of -2 times a plus 8. Notice I have to put that asterisk in there for the multiplication, and I say evaluate. And that's a 1, and notice it doesn't care, it's dividing by a minus 4. It never asks whether a is 4 or not. It just divides by it, and we get this. And now we have to zero these out. And so if I multiply the bottom here by 2a minus 9, the negative of that, actually, the negative of 2a minus 9, and add up here, that'll be a 0. And if I do the negative of a minus 6, that will make that a 0. So I have, I think, both of those. Oh, wait, maybe I don't have both of those in there. So there is the negative of 2a minus 9, and I will copy that, and now I need the negative of a minus 6. Now if you're really brave, you could put in here 6 minus a, because that is the negative of a minus 6. And now we need to do this in row 1. But again, remember we had a minus 6, so I need that negative. So probably the safest way to go is the negative with the parentheses and just rewriting what you had. But again, if you're brave and so forth, you can do the 6 minus a. We'll show that result. And there we get our final solution, which is really something. And so there's our answer, is that x would be this quantity here, y would be this quantity, z would be this quantity. And notice, compared to the text, hey, we go a little better than them, because when they take the case of a not equal to 4, they give the b minus 6 over the negative 2a plus 8, but they just say u and v, and they never tell us what u and v are, okay, for that unique solution. Hey, but we know because we've used Sage Cell and Sage Math, and here we have it. This is what it would be. And actually, if we know a and b, even after we've gotten this expression, we can use Sage to evaluate it after the fact instead of before. So at any, if I told you an a and b, this would just collapse to it if I reevaluated. But also, if you tell me a and b, I should be able to plug those in and evaluate at this stage. Well, actually, we can do that. I'm not going to do it in this video, but there you go. That's example, what the heck example was that? 6, I think? What's the next? Yeah, so that was example 6. So there we go.